All, this is going to be a lecture 6 of chapter 1 on the numerical linear algebra series based on the book by Professor Crefton Lloyd. So this lecture 6 is about projectors, and it's going to be the second part from lecture 6 to lecture 11. And this is based on the theme of orthogonality. What is meant by orthogonality? What is meant by orthogonal matrices? Later we will be introduced one by one, which is a very important concept of numerical linear algebra. And another fundamental related to orthogonality is projection matrices or projectors, which can be orthogonal and non-orthogonal. So let us come. What does mean by a projector? A projector is like a square matrix which it satisfies this property p square equal p. So whichever the one operator which satisfies this property is termed to be as idempotent, and this projector can be orthogonal and also non-orthogonal. So let us now assume that any projector can be of non-orthogonality can be called as an oblique projector. So in a geometrical perspective, what does mean by projections? So if we are to shine a light on the range of P, it is spanned by the columns of P matrix from the just right direction. We don't know the what right direction, so we are projecting it. Then there would be a uh, shadow formed. Then that shadow would be the PV projected by the vector B. So what does this intuition is means will be more clear. For example, B is the range of P. It means it can be expanded by the columns of P. Then if supposedly V is in range of P, then if we are making a shadow, making a projection a light, then applying this operator like a projector, then the shadow will be result in the V itself. In a mathematical sense, for example, if we try to project V using the projector P, then we have this property V can be expanded as Px and coefficient of expansions. Then P square is equal to P, we are going to operate. Then Px is equal to V. That means it's projected onto the itself. That so what direction does the light shine so that V not equal to PV? So if we have some, suppose if V is not in range of P, then the projection of that vector will not be equal to V. Then what this PV minus V is the one what what uh, is what does this mean by that line? So we will be projecting into this V, then the remaining part will be taken by this line called as PV minus V. So what does this mean is P V is in range of P, then PV minus V will be in a null space of P. The both are complementary to each other. So if these spaces are complementary to each other, there is also a projector I minus P, which is a complementary projector to P. And I minus P is also projector because it satisfies this idempotent property. And what does mean by complementary projector in sense? What is the range of I minus P is the null space of P. What is the null space of I minus P is the range of P. So both spaces are complementary to each other because the projectors are complementary to each other, and the intersection is a null set. So what does it all mean is any space in CM can be separated into two spaces which are complementary to each other. It means that intersection will be a null set. One is S1, which can be based on the projector P, and the S1 to be is an S2, which is complementary based on the another PV minus V. It is based on the projection range of I minus P. So these are the complementary subspaces S1 and S2, and S1 is for the projector P, and S2 will be a null space of P, which is means the range of I minus P. So this is the concept it gives by the projector. Yeah, any space of CM can be segregated into two complementary subspaces S1 and the S2. This can be taken, for example, for it can have a very good application. For example, in the last lecture we saw that eigenvectors, and for example, to identify the coefficient of expanse along this eigenvector as a basis, if you wanted to find the component of x in the direction of a particular v, it is related to the problem of the projections. The projector can be computed based on the eigenvector v. It is like a rank 1 projection update that it will be coming to the later part of this video. The second one is what about the special property? What about the projector is an orthogonal? The projector is orthogonal means that the two spaces, complementary spaces, are orthogonal to each other. One important thing is orthogonal projectors not necessary to be orthogonal matrices. The orthogonal projector can also comes from the arbitrary matrices. The only satisfaction needed for a P to be an orthogonal matrix is it should be an Hermitian or a symmetric. P transpose equal to P in the real cases. So, for example, let us form an orthogonal matrix from the orthonormal basis. So this can be formulated for any taking an arbitrary n orthonormal vectors and making a q into q transpose will give you an arbitrary orthogonal projector with using an orthonormal basis. So this is can be more picturized using these equations. For example, any vector can be expanded in term of orthonormal basis, and the remaining thing can be as a residual will be orthonormal to this orthonormal basis. So a vector can be decomposed into a component along the column space of Q plus a component this residual, which is an orthogonal to this orthogonal space. So it means that we can formulate a projection onto this orthonormal basis, which can be each one will be a component along the orthonormal columns, and the orthonormal projection can be comes from this columns of Q. QQ transpose will be the projection P, and that once the PV is projected is termed to be as Y. Then R is orthogonal to this Y. And also we can also make a complementary projection using this concept I minus IQQ transport, and this also seems to be like an orthogonal for the reason that it satisfies the property uh, I minus q also seems to be as a symmetric or Hermitian in a complex case. Now, another important special case about this is rank 1 orthogonal projector, which can be formulated by any single directional vector using this matrix. This is an orthogonal matrix of rank 1. And when the higher class orthogonal, higher rank projector can be computed based on this single rank projector, because the reason is the complementary property. The complementary of this projector is I minus QQ, which has a higher rank. For arbitrary vector, which is not necessary to be a unit vector, we can be able to compute a rank 1 projector, and complementary or higher rank projector can be computed using this 6.11 equations. So projections can also be an orthogonal projector using an arbitrary basis. Previously, we saw the projector can be an orthogonal matrix using a QQ transpose. So from certain from the arbitrary basis, we have an arbitrary independent vectors. Then y is in the range of a. Then y minus v should be an orthogonal to range of a. If we assuming this property, then using this certain linear algebra concepts, then we finally end up that a projector to be an orthogonal matrix can computed based on this equation 6.13. To be noted, if Q is orthogonal, then QQ transpose is equal to identity matrix. Then it end up in AA transpose or QQ transports. So these are something a concept related to orthogonality, projections, and um, how any vector can be projected into a subspace, and how any vector can be represented in a two complementary spaces. One is the projection space, another one is an the residual space, or S2, S1 plus S2. S1 can be projection space, S2 can be a residual space. So if it is an orthogonal, then S1, S2 will be perpendicular to each other. We will be utilizing this concept later in this part of this lecture series. Thank you.